Alright, we've already done a little bit with graphing exponential functions, but let's look at some more examples and maybe some that are a little bit strange. Okay, so we're going to start by finding x-intercepts. Remember, when you're finding an x-intercept, you're just going to set your y value equal to 0 and then solve. So we'll have 2x squared, 2 to the x squared minus 5 minus 16 equals 0. This looks similar to a problem we saw earlier where we had to move a number to the other side. So we'll start by moving that 16 over here. Now, we don't have the same base on each side, but it's not going to be difficult to get the same base on each side. So I feel like that would probably be the best way to do this problem, is to change that 16 to 2 to the 4th power. Now that we do have the same base on each side, all we have to do is set our exponents equal and solve. So that's going to give us values of plus or minus 3. So those are the x-intercepts of the graph. This one doesn't actually ask us to graph it. I think the whole point of this was to see that we are using one of the things we learned today about solving exponential equations to help us find x-intercepts rather than to actually solve an equation. This one's a function instead, right? So it has many purposes to be able to solve an exponential equation, to actually solve an equation or to find intercepts of a graph or various other purposes. How would we find the y-intercept of this? It doesn't ask us to do that, but just for review's sake, let's do 2 to the 0 squared minus 5. We're just plugging in 0 for x, so that would be 2 to the negative 5th power. Oh, this is kind of an ugly y-intercept. So that would be 1 over 32 minus 16. So it would be very close to 15, very close to negative 16, right? Just barely shy of negative 16. That leads me to believe that this negative 16 right here is probably indicative of our horizontal asymptote, because our entire graph is going to move from a horizontal asymptote at y equals 0 to a horizontal asymptote at y equals negative 16, which this y-intercept seems to also agree with, because this point is going to be right above that asymptote, right? All right, moving on. Sketch the graph. Find the x and y intercepts, find the asymptote, use transformations, and plot additional points as needed. Sketch. All right, so I'm just going to start by doing x and y intercepts, because that's a little bit different than the way we did these in section 1. So I'm going to take my equation, 3 to the 2x plus 1 minus 1, set the equal to 0. So that gives me 3 to the 2x plus 1 equals 1. Now here's something really cool, is that 3 to the 2x plus 1 can be rewritten as 3 to the 0. Why is it that I wrote that 1 as 3 to the 0 instead? Why did I just do that? What is anything to the 0 power? Well, it's 1. That's just a really convenient way to get a common base. And then once our bases are common, we can just set this equal like this. 2x equals negative 1, x equals negative 1/2. And we've got our x-intercept. Okay, let's do a y-intercept. So that would be 3 to the 2 times 0 power plus 1 minus 1. So 3 to the first power, right? Because 0 plus 1 would be 1. So 3 to the first power minus 1 would be 2. That's 3 minus 1, which is 2. So we'll have a y-intercept. So this point here was at negative 1/2 is 0. And then this point we plugged in a 0, so we got a 2. So there's our y-intercept. Let's plot those 2 points. So we have a point at negative 1/2, 0. We have a point at 0, 2. Looking at our equation itself, we know that this value right here is our k value, and it's telling us that we're going to go down 1. And what that also tells us is that our asymptote is going to be at y equals -1. So I put that in my graph here. And now it suggests plotting additional points as needed. I don't know if we need any additional points because those two intercepts kind of give us everything we probably need. So I'm just going to sketch through those, and that's a pretty good graph in my opinion. If you wanted to do this whole thing with transformations, this one's a little bit trickier. Let's look at that really fast. I'm just kind of going back to my original problem, but I'm going to factor out the 2. So now you can see this more in our transformation form. This 1/2 means it's going to be left 1/2. And of course we've got the -1, which is down 1. Well, what about this 2, though, that we factored out of this little exponent thing? Well, that 2 inside of our problem, so inside of our exponent, that's going to be where it changes the horizontal stretch or compression. So the 2 would actually be a horizontal, so that 2 right there would be a horizontal compression, which has the overall effect of making the graph look skinnier than it normally would. So a horizontal compression of like 1/2, because the horizontal stuff is always the opposite of the vertical stuff. All right, we have one more graph to look at. I don't know what my computer is doing. Back to where I was. There we are. Okay. So I can go ahead and do x-intercepts, which means I would take my 10 to the 1 minus x squared, set it equal to 0. Uh-oh. This is where I have an exponential equal to a 0 or a negative. So that means there's no solution because we can't do the logarithm of 0 or negative. So there is no x-intercepts. Okay, let's go ahead and do y-intercept then. To do that, I'm going to plug in 0. So that would be 10 to the first power, which is 10. So y-intercept at 0, 10. Let's plot that on our graph. The graph paper I chose for this situation doesn't go up to 10. So we could just count 2s instead. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. What's our k value? Is there an extra number being added after our exponential? There's not, is there? So that should mean that our horizontal asymptote, so k is just 0, right? So our horizontal asymptote should be at y equals 0. Let's sketch that in. Which makes sense because there were no x-intercepts, right? Now the last step is to just find some other numbers. So I'm going to just go ahead and plug in some x values and find some y values. So let's start with 1. That's always a good one. So go 10 to the 1 minus 1 squared, which gives us 10 to the 0, which is 1. Well, interestingly enough, because of the square, if I try that problem again with a -1, I get the same exact answer because the -1 squared and +1 squared are the same answer. Well, this is an interesting graph. So if I go over 1 up 1, I also have a left 1 up 1. This is not going to look like our typical exponential graph. And part of that has to do with the x squared in there, right? So it's going to make it come back down. If we want another set of numbers, maybe we should try like 2. So if I do 10 to the 1 minus 2 squared, then that would be 10 to the 1 minus 4, which is 10 to the -3rd, which is an itty-bitty number, 1 over 1,000. So just by going that much further, over to 2, I've taken my graph clear down to that asymptote. And just like what happened when we squared a negative 1 and got a positive 1, same thing's going to happen if we plug in a negative 2. We'll still just get a positive 4 with the same results. So that's going to be exactly the same answer. This graph is staying symmetric because of that x squared. So, strange looking graph here, but it's going to look something like this.